A transatlantic liner of mass 150,000 tons is travelling with a speed of 15 metres per second when she runs out of fuel. It takes 40 minutes for the liner to stop. Find the force of resistance, assuming it to be a constant acting on the liner. The ship then refuels and takes 20 minutes to return to its full speed of 15 metres per second. Assuming the weight of the fuel is negligible, find the driving force produced by the engines, given that this is also a constant. So we need to calculate the acceleration. So let's make some sort of diagram. So we got our liner. We got the initial velocity, which is 15 meters per second. We got an acceleration, and as it's slowing down, this acceleration will be negative, which will be 0 meters per second. 40 minutes is going to be 40 times 60 seconds, which is 2,400 seconds. And we're going to take that direction as being positive. From our Suvat equations, we know that V is equal to U plus AT. So A will be V minus U over T if you rearrange that. Labelling each one, this is U, this is V, and this is T. So substituting in, we're going to get 0, because V is 0. Minus 15 divided by 2,400, which would be equal to, when you cancel that down, minus 1 over 160 meters per second squared. Now if we draw a force diagram, so here we have our liner, we have a driving force, we have a resistance to that, and we have that A is minus 1 over 160 meters per second squared. We don't, as we're only resolving horizontally, we don't really need to consider the weight or its reaction to the C. So the mass is 150,000 tons, which is, now 1 ton, metric ton, is 1,000 kilograms, so this will be 150 million kilograms. Positive direction being that way. Now, resolving forces horizontally, we note that the driving force this time, minus R, will be equal to MA, because an acceleration of Newton's second law applies. And we also note that however, there is no driving force, so this will be equal to 0, but we will need it to do the last part. So 0 minus R will be equal to 150 million times my acceleration, which is minus 160. So you're going to get minus R is equal to minus 937,500 newtons, and therefore the resistance will be 937,500 newtons. Right, our ship now refuels. It starts at 0, it's going to end up with an acceleration, and it's going to end up at full speed 15 meters per second. It's going to take 20 minutes to do that, so it'll be 20 minutes times 60, which gives you 1,200 seconds. So a little bit care to make sure the units are all consistent. Positive direction, we're going to expect a positive acceleration in this case. V is equal to U plus AT. Therefore, A will be V minus U over T. So this is U, this is V, and this is T. So this time we're going to do 15 minus 0 over 1,200, which is going to give an acceleration of 1 over 80 meters per second squared. Our force diagram, same as before, but this time the acceleration is 1 over 80 meters per second squared. Mass is still the same, 150 million kilograms. So resolving horizontally again, we're going to have D minus R is equal to MA. D we've got to find, we've got that resistance force that we just calculated to be 937,500 is equal to 150 million times 1/80th. So D minus 937,500 is going to be equal to 1,875,000. And therefore, the driving force will be 2,812,000,000 500 newtons. This one, sorry, 2 million. This one should have been 1,875,000. Okay, so the driving force required will be 2,812,500 newtons. Okay, so that once it gets going, there will be that resistance again, which it will need an extra bit to overcome. Okay, so this has been a video to show you how to use some Suvat equations and to find some horizontal, some force diagrams in the horizontal direction in order to get a driving force and a resistance force. Hope you've understood, and I thank you very much for watching.